Well, I'm going to try to do our first video. Section 4.5 talks about limits at infinity. I want to talk about a function. We want to discuss its end behavior. What's happening as x gets very big or x gets very, very small. So by definition, here it says that if L is a real number, then the statement, the limit as f of x as x approaches infinity equals L, means that for every little tiny number, epsilon, there exists some number m such that the difference between the function and the limit, when it's small, then x is getting very big. Look at the picture over here as what's going on as x gets big. What's going on as we go along that way. So that's what we want to talk about, limits. Limits. And so when we talk about limits, we're talking about asymptotes. Asymptotes. And we're looking at horizontal asymptotes. So if, again, it is true that the limit as x approaches minus infinity, or the limit as x approaches infinity of a function equals a number, that means y equals that number, horizontal line, is the horizontal asymptote. And so we're going to look about horizontal asymptotes because we're going to talk about graphing and how we can do that. So how do we find limits? How do we find limits going to infinity? Well, if you have a limit as x approaches infinity of a constant over x to a power. So if the denominator is going towards infinity, then that limit is 0. That limit is 0. Likewise, the limit as x approaches minus infinity of e to the x. Well, that means 1 over e to the x, with if x is approaching minus infinity. So that's going to be 0. And so finding limits. So here's a limit. Find the limit as x approaches infinity of 5 minus 2 over x squared. Well, again, from what we said about limits earlier, that if you have a limit of a sum, it's the sum of each one. So the limit as x approaches infinity of a constant, well, the limit of a constant is always the constant. And then the limit as x approaches infinity of 2 over x squared, that's 2 over a large number, which means that's going to 0. And so this limit is 5. Or the limit as x approaches infinity of 3 over e to the x. Well, if that is a e to the x is infinity, x going towards infinity, we've got 3e to the minus x, and the limit of a constant. Constants always flow to the front. And so we end up with the limit as x approaches infinity of e to the minus x, and the limit of e to the minus x is 0. And so we have found the limit is 0. Finding limits. Finding limits. Now you also have a video that I've put up discussing finding limits. And it's going to talk about a problem like this one. What is the limit as x approaches infinity of 2x minus 1 over x plus 1? What is that limit? What is that limit? Well, we got, again, because it is a quotient, we can talk about the limit at the top and the limit at the bottom. And the limit as x approaches infinity of 2x minus 1 is infinity. And the limit as x approaches infinity of x plus 1 is also infinity. Infinity over infinity. That's the indeterminate form. We've talked about the indeterminate form earlier. And when the indeterminate form is found, there may be a way of finding the answer. We may be able to find the answer. And what we do is we look at the power on the x's. And you'll notice here it's 2x to the first and x to the first. So if we divide numerator and denominator by x, well, they do the same thing, top and bottom. We haven't done anything wrong. That leaves me with the limit as x approaches infinity of x minus 1 over x, 1 plus 1 over x. There's that 1 over x, that limit, okay, is 0. And so we're left with 2. And so we can find limits. We can find limits by evaluating there. For example, each of these. Okay? Each of these. Okay? 2x plus 5, 3x plus 1, x approaches infinity. Well, if we look at the highest exponent term, it's x squared. So we divide everything by x squared. 2x over x squared gives me 2 over x. 5 over x squared. 3x squared over x squared gives me 3. 1 divided by x squared. So I've divided numerator and denominator by x squared. And the limit as x approaches infinity of 2 over x is 0. Of 5 over x squared is 0. 2 over a large number, 0. 5 over a large number, 0. And then 3, the limit of a constant is a constant. And we get 0. So we get a limit of 0. Same kind of problem. Highest exponent is x squared. So we divide everything, numerator and denominator, by x squared. We end up with 2/3. Again, highest exponent here of the denominator, it's always the denominator to look at. Look at the highest exponent of the denominator, is x squared. So if you divide everything by x squared, we get 2x plus x 5 over x squared, 3 plus 1 over x squared. Both of these are 0. This is 3, so 2 times infinity, so infinity over 3 is infinity. So that means the limit does not exist. When we write something equals infinity, it means it does not exist. So here's the guidelines for finding the limit at plus or minus infinity. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. Look at that first example. The degree of the numerator is 1, the degree of the denominator is 2, and so that limit is 0. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. Our second example here, they both are x squared, and so the limit is 2/3. And if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. And so we can look for and try to find limits. Look for and try to find limits. Now, we can't always do it by dividing by that x. So sometimes we have to use some other techniques. And we won't do much with this. But as the limit as x approaches infinity of the sine, or the sine of x over x, we can use the squeezing principle that we used back in chapter 4 and figure out what that limit is. To figure out what that limit is. And so limits of infinity. That's what this section is talking about. Limits of infinity. Right? Trying to find out what is going on and trying to figure out the limit. Now, when we say that, for instance, the limit is x approaches infinity of x cubed, well, that's going to be infinity. What that means is that the function is increasing without bound. There is no limit. There is no limit. Likewise, as x approaches minus infinity, this would be minus infinity cubed. The minus cubed is the minus, so it's approaching minus infinity. Again, it's decreasing without bound. There is not a limit. We cannot find the limit. The limit does not exist. And so here's a relationship. Right? Now, what they've done here is they've done long division first. Okay? Because of the way this setup is. But look at the degree of the top and the degree of the bottom. The degree of the top is bigger than the bottom. That means the limit is infinity as x approaches infinity. Notice here, the degree of the top is bigger than the bottom. So it's going to be approaching infinity. But in this case, because it's approaching minus infinity, the numerator, x squared, is going to be positive, where the denominator is going to be negative. And so it's going to approach minus infinity. It's going to approach minus infinity. So that's finding limits. That's finding limits, looking at. And so in section 4.5, you have an assignment. Check out the assignment, begin to work on it, and we'll talk more about this, and we'll look at the next section in a later date.